Hello, welcome to Biological and Physical Chemistry, topic 1.4, Benzene and Derivatives. My name is Stephanie and I'll be going through the slides with you on this recording. Okay, so let's talk about the learning objectives. So hopefully by the end of this video tutorial, you will be able to describe the structure of benzene, classify molecules using the aromatic definition that Huckel has, understand the increased acidity of phenol compared to aliphatic alcohols, explain why benzene does not undergo addition reactions, describe the mechanism and process of electrophilic aromatic substitution, abbreviated as EAS, explain why certain groups on benzene are classified as activating or deactivating towards electrophilic aromatic substitution, and predict the products from these reactions. Okay, so including the orientation and the reactivity. So firstly, let's have a talk about benzene and the structure of benzene. So benzene is the simplest example of an aromatic hydrocarbon. It's called an arene and it's C6H6. So it's got 6 carbons, and on each carbon it's got 1 hydrogen. So C6H6 means that we must have some sort of double bond within the system. So looking here, we can see that we have our 6 carbons, and if we put a double bond in between every second one in a conjugated fashion, we would have 6 hydrogens. So we've got a conjugated system. So conjugated, remember, is a double, single, double, single, double, single when we're talking about our bonds. So just a refresher on the 2 different types of bonds. We've got our sigma bonds, which is the front-on overlap of orbitals, and we've got our pi bonds, which is done in our p orbitals above and below the plane of that particular element. So to make a, say this is a carbon, to make a pi bond, we would be sharing 2 electrons above and below, so 2 in total. So there'd be maybe 1 below and 1 above. So let's have a look at the structure of benzene again. So we've got our 6 carbons, our 6 hydrogens, and we've got our double, single, double, single, double, single. So we can have the double, single, double, single, double, single like this, or we could have them like this. So there is a subtle difference between these 2 structures. So if I count this as carbon 1, 2, 3, 4, 5, 6, we have a single bond between 1 and 2, a double bond between 2 and 3, a single bond between 3 and 4, a double bond between 4 and 5, a single bond between 5 and 6, and a double bond between 6 and 1. If I now look at this structure, and this one's still carbon 1, we have a double bond between 1 and 2. Okay, whereas before we had a single bond, and it continues on. So there's a subtle difference, and the difference between these 2 is called resonance. Okay, so the 2 different structures are resonance structures. So looking at it from the pi bonds only now, so we can see that we've got a pi bond 1, 2, 3 versus 1, 2, 3. So it's a bit easier to see the differences between those. So this is demonstrating benzene in the localized electron model. So we're saying that those electrons exist between these 2 carbons. So reality is that the electrons are not localized, they're in these big clouds, and it's probability based, and we've found that delocalized electrons is a better way of thinking about electrons. They're all incorrect, but it's the most correct one that we have at the moment. So we can abbreviate our benzene ring when we draw it on a bit of paper to look like this. So it's a circle in the middle indicating the delocalized electrons. And we could abbreviate it like this. So it looks kind of like a donut to me. So we've got the delocalized electrons above and below the plane of the benzene ring that's in the middle. And these delocalized electrons are hugely stable. They do not want to react. Okay, so they're really, really happy. They don't want to react, and we will talk a little bit more about why they don't want to react. So you've probably heard of the term aromatic before. So aromaticity. So something that is aromatic originally was defined as something that had a smell, so a particular smell. So it was aromatic, it had this really nice smell to it, or this really bad smell to it, but that is what we talked about originally. Over time we have come up with this Eric Huckel's definition, so Huckel's definition, and that's how we characterize things as being aromatic. So first of all, the molecule must be planar. It must have at least one unhybridized p orbital. So to have one unhybridized p orbital, it must not be more than sp2. So sp2 is kind of like our ideal Goldilocks for Huckel's definition. And we must have 4n plus 2 pi electrons. So n needs to be an integer, so 0, 1, 2, 3, or 4. So 4n plus 2, so if n was 1, we would have 4 plus 2, which would be 6 pi electrons. So 6 pi electrons, a planar molecule, and sp2 would be a beautiful aromatic compound. Aromatic compounds are very stable. They do not like to react because they have these delocalized electrons within their structures. So let's look at some examples. So we got pyridine, which is a very smelly compound. We've got pyrimidine, we've got pyrrole, and we've got imidazole. So they're all aromatic compounds, and let's have a look at each of them and work out why they're aromatic. So pyridine, we have 2, 4, 6 electrons in the pi bonds. So showing that in this diagram, we've got 1, 2, 3, 4, 5, 6. These 2 electrons of the nitrogen, the lone pair, are not in the pi orbital. They're sticking out of the plane. So we've got a planar molecule, we've got 6 pi electrons, which fits our 4n plus 2 rule. It's planar, and each of these are sp2. So they've got those pi electrons free. So that one's aromatic. This one here too, we've got 2, 4, 6. So we've got 1, 2, 3, 4, 5, 6 pi electrons. They're all sp2 and it's planar. This one here we have 2, 4, 6. So notice that I'm now counting the nitrogen lone pair of electrons when I'm doing my 2, 4, 6. The reason for this is now this nitrogen has a bond to a hydrogen. It's pushing those pi electrons, those lone pairs, into the pi orbital, to the p orbital. So we've got 2, 4, 6 now. Okay, so this one here, we've got one nitrogen that's not bonded to anything, and we've got one that is. So these 2 would be included, and these 2 would not be included. So we've got 2, 4, 6, 2, 4, 6. They're all sp2 still, and we've got those electrons sticking out of the ring, and it's planar. So they're examples of some common aromatic compounds. You've probably recognized a few of them. So when we come to benzene and benzene derivatives, we have lots of common names. So it makes the nomenclature a little bit more challenging. Generally, there's more than one name for the different compounds. So there's a few different ways of using our UPAC nomenclature to piece the puzzles together. Generally, if there's a common name for it, so such as toluene, which is a benzene ring with a CH3. There's phenol, benzene ring with an OH. There's aniline, a benzene ring with an NH2. We've got acetophenone, okay, which is a benzene ring with a methyl ketone. We've got benzaldehyde, which is a benzene ring with an aldehyde. We've got benzoic acid, okay, and we've got benzonitrile. They're the most kind of common ones. If there's a common name for it, you can use that name as the higher priority. So that name is the highest priority. And then you put your substituents off the ring that aren't part of the the common name alphabetically out the front. Okay, or you can go back to first principle and just use IUPAC nomenclature, where you just call the molecule a benzene. So you put all the substituents out the front and you call it a benzene. So in terms of our ring structures, so 1 ring structure is a benzene, 2 is a naphthalene, and 3 is an anthracene ring. Okay, and this is taken from McMurray. Okay, so let's just have a look firstly at some common aromatic compounds, and then we'll go into practicing our nomenclature. So one key thing that's kind of tricky and hard to remember, but one key thing to remember is if you have a substituent and it's just a benzene ring, it's called a phenyl group. If you have a substituent and it's benzene ring with a CH2, it's a benzyl group. Okay, so phenyl and benzene, so phenyl and benzene. Benzyl, phenyl and benzyl, phenyl and benzyl, they're different. Phenyl is a benzene ring, benzyl is a benzene ring with a CH2. So try and remember this. It will come up throughout the remaining topics. Okay, so let's have a look at some common aromatic compounds. We've got vanillin, which has a aldehyde, an ester and an alcohol coming off it. We have styrene, okay, we have aspirin, which we've made now, so we've got our carboxylic acid and we've got our ester. We've got 2 carboxylic acids on this structure here. We've got alcohols, and we've got carboxylic acid, which is benzoic acid, which is actually a fungicide. So there's some common aromatic compounds. And you can see that these common aromatic compounds have some interesting common names. But when we come to our nomenclature, we're going to use the IUPAC nomenclature. Before we learn how to use the IUPAC nomenclature, we need to know the positions on the benzene ring. So if you have more than one substituent, you'll have to refer to how that substituent is related to the original substituent. What do I mean? Let's have a look. So if we have a benzene ring with any kind of group, so it could be a CH3, it could be an NO2, some kind of group coming off it, the group coming off it must be the higher priority, and then you can refer to the lower priority as a substituent, depending on where it's bonded. So if it's directly opposite, it's ortho. So it could be opposite on either side. So this position here, anything bonded off that carbon or that carbon would be ortho. The next one over is meta. Okay, so meta on either side, meta. And I personally remember that because you can draw an M. There's an M position. Okay, and then we've got para. So para is opposite your original substituent. So let's have a look at some examples. So our parent molecule toluene, we're brominating the compound. We'll learn about these reaction conditions a little bit later on. So we've got our toluene, and then we've brominated it, and it's in a para position. So it's para-bromotoluene. Now we have our benzene ring, and we have 1, 2, 3, 4. So our CH3 is the higher priority compared to the bromine. So we've got 1, 2 dimethyl, 4 bromo. Alphabetically comes out as 4 bromo, 1, 2 dimethyl benzene. So looking at our next one, nitro is the higher priority out of nitro and chlorine. So we've got a 1, 4 dinitro, and numbering it, you would put chlorine on position 2. So alphabetically, it'd be 2-chloro, 1,4 dinitrobenzene. The next one over is a very explosive molecule. So we've got our toluene. Okay, so our toluene parent group, and then we've got our 1. So we've got our 1, 2, 3, 4, 5, 6. So it's 2, 4, 6. Trinitrotoluene, which is TNT. Okay. So let's have a look a little bit more about how to do the nomenclature. So there's lots of variety in it, but our priorities in our functional group, so looking at our parent molecule and that first substituent, if it's a CH3, it's toluene. If it's an NH2, it's aniline. If it's an OH, it's a phenol. If it's an aldehyde or carboxylic acid, it's benzaldehyde or benzoic acid. So carboxylic acid is the highest priority, benzaldehyde, alcohol, NH2, methyl. So looking at this molecule here, there's quite a few ways we can name it. We can use the phenol parent group. Okay, so a benzene with an OH is a phenol. And then we could say ortho-hydroxyphenol, or we could say 1,2-dihydroxybenzene if we want to use the fact that we've got a benzene ring with 2 OHs coming off it, or we could say ortho-dihydroxybenzene. So there's a little bit of variety in the nomenclature with these compounds. So this one here, same compound, but we now have a meta position, and this one we have an ortho position. Okay, so looking at something a little bit different that doesn't have 2 OHs, so now we've got an OH and an NO2. So NO2 is not on our functional group priority list, but the OH is. So it would be a phenol, and we have a meta-nitro. So it'd be meta-nitrophenol. This one here, we've got an aldehyde, we've got a phenol. So aldehyde and phenol, so it'd be benzaldehyde. And we would go 1, 2, 3, 4. So it'd be 4-hydroxy, 3-methoxy, benzaldehyde. This one here, we have a phenol and a toluene, so the higher priority is the phenol. So it'd be a para-methylphenol. Okay. So let's have a go at doing some of our own. So I'll give you a little bit of time to have a look at these before I talk you through them. Okay, so let's have a look at the first one. So we've got a CH3, so that would be our toluene. So we've got a toluene with a nitro, and they're ortho. So it's ortho-nitrotoluene. Oops, sorry. Ortho-nitrotoluene, or you can use these two names if you prefer. This one here is a para position to each other, and it's a 1,2, so it's a dibromo. So it's a para-dibromo benzene. This one is a meta position to each other. We have a phenol or a toluene. So phenol actually has the higher priority, so it would be a meta-methyl phenol. This one here is a little bit more complicated, so we actually have a 1, 2, 3, 4 carbon chain with a chlorine, a methyl, and a phenol coming off it. So the reason that this isn't the highest priority is because this carbon chain's longer, so we name from that. Another way of looking at it is this carbon chain has a halogen coming off it, so if we start naming from this, it'd just be impossible to try and work out how to name it. So we go 1, 2, 3, 4, so 4-methyl-butane, butane, okay, and we've got a chloro, methyl, and a phenol. So it'll be 1 chloro, 2 methyl phenol, butane. This one here, we've got an aldehyde or a alcohol, so the aldehyde's the highest priority, so it'll be a meta-hydroxy benzaldehyde. Okay, so these are a good example of the sort of nomenclature that we will be talking about for these types of compounds. So quite simple molecules and they should be quite easy for you to name. So now let's have a look at the acidity of phenols. So this is actually a very interesting slide. So phenols, remember, are a benzene ring with an OH group coming off them. So that benzene ring has that cloud of delocalized electrons above and below the plane of the actual benzene ring, and we have an OH coming off it. In an aqueous environment, we get this phenoxide ion that's formed. So we get the deprotonation of that OH to the O minus, and we get H3O plus. So this O minus is extremely stable because we have those delocalized electrons which can add to contributing more resonance structures, and the more resonance structures you can deduce for a particular compound, the more stable the compound is. So let's have a look down here. So we've got our phenoxide. Here we've got it again. So if we were to move all these electrons over one, that would give us another resonance structure. So we've got 2. We can then kick down those electrons from the negative charge to make a carbonyl, and then by doing that we're going to have to break this double bond and put the electrons onto this carbon. So then we'll get a ketone and a negative charge on this first okay, so that'll be 1 to the second carbon. We can then have those electrons go back into the ring and make a double bond, and those electrons going on to the paracarbon. Okay, and then we can have the last one going back in, and that one going on to the ortho again. So we've got 1, 2, 3, 4, 5 possible resonance structures. So that phenoxide ion is very, very stable because of those delocalized electrons and the 5 structures you can come up for the resonance. When you compare that to your cyclohexanol, okay, so we've got no delocalized electrons, we've just got this OH. When it forms the cyclohexoxide ion, there's no way to stabilize that negative charge. There's no extra electrons to help out carrying that. So the equilibrium actually lies towards the cyclohexanol. Whereas in this case, it lies towards that phenoxide ion. Okay, so let's have a look at how the substituents coming off the benzene ring can affect the acidity of that phenol. So to make a phenol acidic, okay, so an acid gives up a proton. So to make this phenol give up that proton, we want to make that OH bond, that phenol OH bond, weak. We can do that by pulling the electron density away from that OH bond and back into the benzene ring, and that will make that O minus come about better. Okay, so we'll be stabilizing that O minus. So depending on the groups that you attach to the ring, you can stabilize that O minus. So if we have groups that are electron withdrawing, so they're attached to the benzene ring, they're pulling electrons from the benzene ring, you can kind of think of it, so you've got your oxygen here, so we've got our O oxygen, we've got our electrons being pulled away onto these NO2 groups. It's going to be really destabilizing that OH bond. That would make it very acidic. Okay, so the NO2s, when we have 3 NO2s, is actually quite strong acid, so it's 0.5 is the pKa. If we go down to 2, so less of a pull, we're at 4 for the pKa, and if we're down to 1, we're at 7. Okay, so NO2s are very electron withdrawing compared to chlorine. Okay, so they're slightly more electron withdrawing than chlorine. Chlorine still, as we know from last week, is electron withdrawing. They're very good for that. So you can see there's only a slight difference in the pKa, but it is a substantial difference. Groups that are not electron withdrawing, that are the opposite electron donating, are things like carbon groups, so CH3 or any sort of aliphatic chain. So you can see the pKa is a lot higher, so it's a weaker acid. and phenol with nothing on there, it sits at 10. Okay, remember, like we said last week, the smaller the pKa, the stronger the acid. Alright, so if you want to pause the video and have a go at doing these ones here. So what we want to do is have a look at these phenols and order them in their acidity. So which one's the most acidic and which one's the least acidic. Okay, so let's have a look. So from the slide we looked at before, we know NO2s are the most electron withdrawing compared to chlorines, and hydrogens are not electron withdrawing. So remember, we want to destabilize that OH bond and make that O minus, so that hydrogen's going to go away. How do we do that? We do that by pulling the electrons away from that. So we want groups that are electron withdrawing. So the most electron withdrawing group is your NO2, and this compound has 2 of them. So this would be the most acidic. This one has 1 of them and 1 chlorine, so it'll be the next. This one has 2 chlorines, still very acidic. Phenol, not very acidic. Okay. So you'd go 1, 2, 3. Okay, so let's have a talk about why benzene does not undergo addition reactions. Okay, so I've got a beautiful diagram here to help us out with this one. So benzene, remember, has beautiful delocalized electrons. It's very, very stable. It's aromatic. If you were to mix it with Br2, okay, for an addition reaction to occur, you would have to use some energy to break the delocalized electrons and add on the bromine. Okay, so you get this intermediate. So you'll have a slight drop in energy when the intermediate's formed. At this position here, we could have another bromine add-on, so Br minus come into this positive charge and get an addition reaction, but our energy would end up here. So our overall delta G, which we'll learn a bit more about when we talk about thermodynamics later in the course, our overall delta G would be using energy. Okay, so it's not a favourable interaction. If we were to remove this proton and put those electrons back in and reform that hugely stable aromatic ring, then we would have a decrease in energy. So the overall energy would be favourable. Okay, so the substitution, we're not breaking those delocalized pi electrons. They're really, really happy. Whereas addition, we're breaking that aromaticity, those delocalized electrons, and it just does not occur. So benzene is different compared to alkenes. Okay, so even though there's double bonds, they're delocalized electrons, so they don't do addition reactions. Okay, so let's have a look at electrophilic aromatic substitution. So we've got our benzene ring here, we've got a hydrogen that's indicated on it, we've got an electrophile, some kind of catalyst. So the catalyst is there to generate the electrophile, and we have the electrophile adding onto the ring and the hydrogen coming off the ring. So they're swapping places, they're substituting. So the mechanism proceeds with the electron-rich pi cloud, so those delocalized electrons attacking the electrophile. Okay, so we have the breaking of the pi electrons to add on the electrophile, and then we have a positive charge on this carbon. So why do we get that positive charge? So we've now got 4 bonds coming off where this hydrogen is, and we've only got 2 plus our extra hydrogen, so we've got 3. So we've got 1 bond too little. Okay, so we've got a cation that's being produced. That cation is stabilized through the benzene ring, so it can jump onto the different carbons, and this can be drawn as the wheeling intermediate. So we can just draw a plus in the middle with our delocalized electrons, or you can just draw out one of these structures. Okay, so once it's formed, it doesn't hang around, it gets used up really, really quickly. So as soon as it's formed, it's reacted straight away. So what happens is the hydrogen is removed and those bonding electrons go back into the ring to give you that aromatic delocalized electrons. And we now have the electrophile in the position of the hydrogen atom. So this first step, producing that carbocation intermediate, is the slow step. Okay, so that limits how fast the reaction is going to proceed. So it's our rate limiting step, which we'll talk about again in topic 2 later in the semester when we talk about reaction kinetics. And as soon as that carbocation intermediate is formed, it's used up really, really, really fast. So the second step is our fast step. So let's have a look at the reagents and the electrophiles of some common EAS reactions. So we've got halogenation, nitration, and sulfonation. Okay, so they're generating new functional groups onto the ring. So if we have a benzene, we mix in some Cl2 and our catalyst is FeCl3, we would swap our hydrogen for our chlorine. So our electrophile is what is adding on, so it's Cl minus. So it's a chloronium ion. So we're getting a chloronium ion adding on to our benzene ring if we have FeCl3 and Cl2. So for nitration we use sulfuric acid, so H2SO4. Sulfuric acid helps to generate our nitronium ion from HNO3. So it forms NO2 plus in situ, which is then the electrophile that's added onto your benzene ring. Our sulfonation is SO3 with H2SO4, and we form HSO3 plus. Okay, so SO3H is what's added onto our benzene ring. So the last two reactions generate new carbon-carbon bonds. So they're the Friedel-Crafts reactions, and we've got an alkylation and an acylation. So the alkylation is adding an alkane chain, so some sort of carbon chain onto it, and an acylation is adding a ketone carbon chain. So let's have a look at the alkylation first. So our catalyst in the Friedel-Crafts is AlCl3, so aluminium chloride, and then our group that we're adding on with usually a chlorine or some sort of halogen attached. The electrophile we're generating here is R+, so it's the alkyl carbocation, and that is what's added onto the ring, just the R. In the acylation, our electrophile that we generate is the acylium ion. Okay, so it's the carbonyl with a positive charge, and that's what's added onto the benzene ring. So we've got 5 reactions here. We've got 3 reactions that introduce functionality and 2 that introduce new carbons onto the benzene ring. So let's look at the mechanism. So firstly, let's have a look at the halogenation. So we've got our bromine that we're adding on. So we've got Br2. Our catalyst is FBr3, and in situ that forms Br plus and FeBr4 minus. So this Br plus is our electrophile. The ring breaks, adds the electrophile, and then our proton is removed by the FeBr4 anion, and the bonding pair of electrons kick back in to make the delocalized electrons again. So we've got the bromine there. With our Friedel-Crafts, this is an alkylation reaction. We've got our catalyst, which is AlCl3. We've got our chlorine that's added on. In situ, the chlorine is removed when we get a positive on this carbon. So we get CH3CH3 and AlCl4 minus. So again, breaking those pi electrons, adding on the electrophile. We then have the catalyst that's now negatively charged because it's picked up an extra chlorine, removes that proton, and those bonding electrons kick back into the benzene ring. Okay, so we've got our rearomatized compound with our alkyl group added on. Okay, so let's have a look at what happens if you do one of these reactions but you already have something substituted onto the benzene ring. So we have a mono-substituted benzene ring under our particular reaction conditions. So what's on the benzene ring will affect the reactivity of that second substitution. So the substituent may make the reaction happen faster, or it may make the reaction happen slower. So for example, our reactivity, so this red where the arrow is this way, is saying that it's very reactive, and the blue means it's not very reactive. So if we have an NO2 group, which is really pulling electrons away from that benzene ring onto itself, it's electron withdrawing, then we would have a deficit of electrons available to then go and attack that electrophile in the first step. So it's quite a slow reaction. Chlorine, similar sort of character, so it's not the best. As we go to our normal benzene, that's our reference point that they've indicated the rate at 1. And as we go over to an alcohol group, so a phenol, the lone pair of electrons on those oxygens will push into the benzene ring, making more electrons available for that first step to occur. So those electrons attacking that electrophile. These substituents affect the reactivity, but they also affect where the second group is going to add on. So if we look at adding on so a nitration reaction, so we've got HNO3 and sulfuric acid, we're going to add on our NO2 as the electrophile. If we have a phenol, the phenols are ortho-para directing. So if you do the reaction, you get 50-50 ortho and para. Okay, so pushing those electrons in, we get 50-50 ortho-para. Benzonitrile, so we've got a C triple bond N, is different. It makes pretty much most of it go into the meta position. Okay, so the substituents direct the orientation as well as influence the reactivity. Now, good news is you don't have to remember what substituents do what. You'll be given this activating or deactivating table in the exam. Okay, so you'll be given this table in the center here in your exam to use. So you need to learn how to use it. Okay, so there's a few things to take away from this. We have compounds on here that are very reactive and ones that are not very reactive. So these ones here would react fast, okay? These ones would react slow. So if you've got a benzene with an NO2 versus a benzene with an NH2, the NO2 one will not react fast, but the NH2 would react very fast, okay? Also take away the direction of the substituent that's adding on. So all of these ones here are meta directors. So they direct things into the meta position. Doesn't matter what it is, it will go in the meta position. This one is ortho-para as well as this one being ortho-para. So the rest is ortho-para and these ones are meta directing. Okay, so all meta directing groups are strongly deactivating. Okay, so their strong desire for electrons pulls electrons away from that benzene ring onto itself. Okay, and it's pulling those electrons away from the benzene ring and making them less available to attack the electrophile. Okay. Things that are activating are pushing electrons onto the benzene ring, so there's more electrons available to, or electron density available to go and attack that electrophile. Okay, so that's our two kind of differences. We've got deactivators and activators, and the deactivators generally are meta-directing, whereas the activators are generally ortho-para-directing. Okay. So 3 types of substituents. Okay, we can have electron donating, electron withdrawing, Okay, so these reactions illustrate the 3 main types of substituents. So what do we mean? So the 3 main types, we've got the blue, which are meta-directing activators, we've got the green, which are ortho and para-directing deactivators, and then we've got the pink, which is ortho and para-directing activators. Okay, so we've got meta-directing deactivators, we've got ortho and para-directing deactivators, and we've got ortho-para-directing activators. So these are the 3 classes. So the first one, we have the electron donating group. Okay, so it's going to be donating group electrons into the benzene ring, and if we do a chlorination, halogenation on that, we will get our ortho para substitution as the majority. So we still get a little bit of meta, but majority of it is in that ortho-para position. So the next one we have is a deactivating electron withdrawing, so we get a halogen. So it's electron withdrawing, but it's not hugely electron withdrawing in comparison to some of the bigger electron withdrawing groups that we have on our table. And this one again is an ortho-para directing deactivator. And we have our electron withdrawing that's, we've got a carbonyl in here, so it's really electron withdrawing, and it's deactivating, so it directs into the meta position. Okay, so we're still getting a little bit of the other ones, but majority of that really is in that meta position. So this is not something you need to remember. This is not something you need to remember. This is there in case you're interested in why they are directing in these directions. So if we have a phenol, so we've got a benzene ring with an OH. If we have ortho attack, okay, so if we break this bond and we have something adding onto the ortho position, we have a very stable intermediate that's formed. Okay, so we've got this carbonyl that's being formed with a positive charge going on there. If we have meta attack, the intermediates that are formed are not as stable. Okay, so this one we've got 1, 2, 3, 4 possibilities. This one we've got 1, 2, 3. Para we've got 1, 2, 3, 4. So ortho and para would be the majority of your product because they're more stable intermediates, because there are more resonance structures. Okay, so OHs, NH2s, chlorines and bromines are ortho para directors, and you'll be given this information in the exam. Okay, so our meta directors, so let's have a look at benzaldehyde. So we've got benzaldehyde, we've got a carbon positive here, okay, and a negative there, so it's pulling those electrons away from the ring, deactivating the ring. Okay, so we've got deactivation occurring. It's going to be forming it into, pushing it into the meta position. And why is this? So let's have a look at our intermediates. So we've got a very unstable intermediate here and a very unstable intermediate here. So we've got a carbonyl, carbon, which is a delta positive with a positive next to it. Okay, very unstable, very unstable. So we've really only got two good stable resonance structures for these two, whereas we have three for the meta. So that's why a majority of it will go into the meta position. And again, your meta deactivators are those ones with the carbonyls or triple bonds coming off it. Okay, so let's do a little bit of concept check. So what products would you expect from the bromination of aniline? Okay, so I've got aniline here. Our bromination reaction is going to occur. So I'll give you a little bit of time to think about that if you want to pause the video. Okay, so our bromination reaction, what are our bromination conditions? We will have Br2 and FeBr3 as a possible combination, and we would have full bromination of that. NH2, how does that activate or deactivate the ring? So looking at your table, NH2 is very, very reactive. It's right up near the arrowhead, and it is an ortho para directing activator. So it activates that ring towards reactions occurring, and it's going to be ortho para. So what's going to happen is if you have an excess of bromine there, we're going to get the ortho positions full and the para, and it's such a reactive system that you would not be able to stop that reaction from occurring. Okay, so have a look at your substituent reactivity table and just make sure that you understand where we're getting that information from. So the NH2 is highly reactive, it's right near the tip of that arrow, and we've got the bromines adding, it's ortho para directing, so all the ortho para positions will be completely filled on that molecule. Okay, and there's some text for you to read about it. Okay, so electrophilic aromatic substitution occurs in biological molecules. So an example is the hormone thyroxine, which is synthesized from an amino acid tyrosine, and it needs iodine for this to occur, hence why iodized salt is so great for you. So I know it's a little bit blurry, but if you can bear with me on this, this is what our tyrosine looks like, and this is what our thyroxine looks like. So we've got a benzene ring that has a hydroxyl coming off it, okay, and then what we want to do is add these iodines to it and link two together. So we have our tyrosine and tyrosine, two of them linked onto our binding site. Okay, we have iodine come in, we have the iodine adding on to the ring. Pardon me. So iodine would, okay, so we've got a OH, so we've got ortho para directing, okay, with the OH there. Our para position is full, so it will go into the ortho position. Okay, so now we've got our ortho double iodines on both of them, and that's because that OH is so reactive, it will just fill up. The next thing we have is, after we have our electrophilic aromatic substitution, we then have a reaction that is catalyzed by H2O2, and we have the rings reacting together in a different way. Okay, so the interesting thing is we firstly have that electrophilic aromatic substitution reaction occurring to make our thyroxine. Okay, so lastly, organic dyes. So colours in compounds can come from two different places. They can come from transition metals, which we'll talk about in a later topic. It's actually a very exciting topic, and it's really, really cool chemistry. Or we can get colour, okay, so transition metals, or we can get colour from our conjugated pi systems. Okay, so large conjugated double bond systems such as those found in organic dyes. So they're extensively delocalized electron systems, and the explanation for these colours rely on molecular orbital theory, which is our last, near the end of the semester, molecular orbital theory, and we'll be talking about HOMO and LUMO energy levels. And the more conjugated the system is, the closer the gaps between HOMO and LUMO. Okay, so our HOMO-LUMO gap, if we have a really conjugated system, the gap's really, really small and the electrons can jump between them and we have a coloured compound. And if we have a non-conjugated system, they're really big HOMO-LUMO transitions. And we'll talk about this later in the semester. Okay, so conjugated systems such as aromatic compounds are very, very common in organic dyes and having colours. So let's have a quick concept check. So if you want to pause the video, you can again have a go at these reactions and predict what the products would be, and I'll go through them in a second. Okay, so what we have now is we have a Friedel-Crafts alkylation. We have a chlorine, so we want to look at how chlorine is going to direct this reaction. So chlorine's in the middle for reactivity and it's ortho-para directing deactivator. So it's going to be an ortho-para director. So we'll get a mixture of ortho, so a CH2CH3 coming off the ortho and coming off the para. So the reason we don't get ortho and para coming off the same molecule is the reactivity is towards the center of that reactivity graph. Okay, so we would get one ortho and one para. So the next one, we have a carboxylic acid. So this is a meta-directing deactivator. We're adding on an NO2 group with these conditions. Okay, so we would just get one meta product. The reactivity is very, very slow for that reaction. So the next one here, we have an OR. Okay, so where is OR? OR is next in the red region, so OCH3 is an example, and this one is quite a quick reaction, ortho-para directing. What we're adding on is a carbonyl with a CH2CH3, so we're going to get it in the ortho and para position. The reactivity is quite fast on that one, so you may even find that you get multiple additions of these ortho-para positions. Okay, the last one is a nitrogen compound, an NR2. So NR2 would be similar to your NH2, so in the red area again, NH2 would be pretty similar. So it would be an ortho-para directing sulfonation. Okay, so ortho-para. Again, highly reactive, you'll probably have ortho and para all filled up on the same molecule. Okay, and this is the references that I've used for creating these slides. So thank you again for listening to my lecture recording. I hope it's very useful for you. It did take me 3 attempts because I did forget to press record, so hopefully this one wasn't too concise for you and I did include enough information in there for you. again, thank you very much for listening. Happy studies, and come and see me if you have any questions.